programming. Now, what is the definition of dynamic programming? Dynamic programming is an algorithm solving technique, and this technique is used to solve optimization problems. Now, what are the optimization problems? These are the problems which require us to calculate the optimal solution to a given problem. Now, using dynamic programming, we can divide a problem into sub-problems and acquire an optimal solution for that given problem. So, this problem or this programming technique or algorithmic technique, it also solves the problem of overlapping solution. The problem of overlapping solutions. So what is this overlapping solutions? We'll be discussing this with the help of an example. Right. So using dynamic programming, we can solve a problem and obtain an optimal solution to it. So this is what is meant by dynamic programming. There are no proven procedures or methods or fixed procedures. For dynamic programming, we do not have any fixed procedures to solve the given problem. We have to solve a given problem using dynamic programming in terms of various stages. So at every stage, we make a certain decision, and at the final stage, we reach the optimal solution to the given problem. This is what is meant by dynamic programming. So this overlapping solutions, this problem of overlapping solutions generally occurs when we use recursion to solve a given problem. When we use recursion to solve a given problem, where one particular functionality is called multiple times to solve that problem. So we'll discuss this with the help of an example, and we'll see how dynamic programming is used to solve this problem of overlapping solutions. We'll see an example of Fibonacci series. We'll see an algorithm which displays the nth Fibonacci number from the series. So I'll write an algorithm. So this is an algorithm which displays the nth Fibonacci number in the series. So if I pass the value of n as 5, it will display me the nth Fibonacci number. If I pass the value of n as 10, it is going to display me the 10th Fibonacci number. So this is the algorithm which does that job. So how does the Fibonacci series look? That's 0, 1. So these two numbers are added. 1 plus 0 is 1. Then these two numbers. 1 plus 1 is 2. Then 2 plus 1, 3. 3 plus 2, 5. 5 plus 3, 8. 8 plus 5, 13, and so on. So according to this particular algorithm is designed. As you can see, the function fib is called recursively for n minus 2 and n minus 1. So this is n minus 2 and this is n minus 1. So addition of these two numbers is going to give me the next term, like 13 plus 8, 21. So that is why it is n minus 2 and n minus 1. So addition of this is going to give me the next term. If I want to calculate the next term, then this is going to be n minus 2, this is going to be n minus 1. Okay. So this is how Fibonacci numbers are generated. So let's trace it out. Let's see how solutions or sub-problems get overlapped when we use recursion technique to solve a given problem. I'll take the value of n as 5. We'll take the value of n as 5. Let's see. N value is 5. Is n less than or equal to 1? No, this condition is false, so it will come over here. So this Fibonacci function is called recursively for n minus 2 plus n minus 1. So it's going to be fib of n minus 2. 5 minus 2 is 3, and here it will be fib of 4. N minus 1 is 4. 5 minus 1 is 4. Next, it will pass the value 3. It will come back here again. It will check n less than or equal to 1. No, condition is false. It will come down over here. This recursive call. First, it will solve the left hand side, then the right hand side. So again, it will be split into two parts. So this is addition operation here. So it will be fib n minus 2 is 1. N minus 2 is 2. N value is 1. So it will come down here again. If n less than or equal to 1, yes, condition is true, then we are returning n. So here in this case, n value is 1. So the result of this will be 1. The result of this will be 1. Next, fib of 2. So it will be split again into two parts. Fib of 0 and fib of 1. Fib of 0 and fib of 1. Next, n value is 0 over here. N value is 0 over here. N less than or equal to 1. Yes, condition is true. So it will return the value n. So this is 0. Here again, fib of 1. N value becomes 1 over here. N less than or equal to 1. Return n. So this will be 1. So this is addition operation which will be performed over here. 1 plus 0 is 1. It will be returned here. This value is 1. Next, 1 plus 1 is 2. So fib of 3, here it will be returning 2. Coming to the right hand part. Again, fib of 4, n less than or equal to 1. Condition is false because n value is 4. Recursively, this function will be called for n minus 2 and n minus 1. So fib of n minus 2. N minus 2 is 2. Fib of 3. Let us solve this left hand side first. So again, it will be split into two parts because n is not less than or equal to 1. So it will come down here to the recursive call. Fib of 0 and again fib of 1. Come down here to the left hand side. N value less than or equal to 1. Condition is true. Return n. Right hand side, less than or equal to 1. Condition is true. Return n. Addition operation of these two things. 1 plus 0 is 1. Coming to the right hand side, fib of, this will be 1 and this will be fib of 2. Fib of 1 is 1. Fib of 2 again will be split into fib of 0 and fib of 1. That is n minus 2 and n minus 1. Addition operation again. 1 plus 0 is 1. This is 1. So 1 plus 1 is 2. 2 will be sent here. 2 plus 1 is 3. So 3 will be sent there. 3 plus 2 is 5. So Fibonacci of 5 is 5. So this is how you draw a recursion tree for a given problem. I have drawn a recursion tree for calculating the nth Fibonacci term. So for Fibonacci of 5, it is going to be 5. Now if you observe closely over here, there are certain function calls which are repeated over and over again. Or you can say that they are overlapping. We have taken a problem and we have divided it into sub-problems. So when these sub-problems are observed carefully, you can see some of those function calls are repeating. Which are those? Fib of 1, fib of 2, fib of 0. Then again here if you see it is fib of 1, again fib of 2, fib of 1, fib of 1, Fibonacci of 2, Fibonacci of 0, Fibonacci of 1. So these many times one particular function is getting repeated. So this is what is called as sub-problem overlapping. We have calculated the value of Fibonacci of 1 over here, but again we needed to calculate it here. We have already calculated the value of Fibonacci of 2, but again we had to do it here. So how many times this Fibonacci function is being called? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 times this recursive function is called due to this function overlapping. This is where dynamic programming comes into picture. We need to solve this issue of calling those same functions over and over again. We need to stop recalculating what has already been calculated. So here dynamic programming comes into picture. So dynamic programming, what it does is, the values which are calculated, the values that are already calculated, they are stored in the form of a table, or you can say array. They are stored in the form of a table or inside array. So whenever the same sub-problem occurs, whatever is calculated will not be recalculated, because the value of that particular function is already present inside this table or array. So whenever, now we have calculated fib2 over here, the value of fib2 is 1. So again when we encounter Fibonacci of 2 over here, we need not calculate it again. The value 1 will be fetched from this table or this array. This is how dynamic programming works. Let's see how to do it. We'll take a table and we'll store the values of these sub-problems. So storing values of these sub-problems is defined as memoization. Is termed as memoization. Let's see how it works. I'll take an array or a table with index values 0, 1, 2, 3, 4, 5. Initially this is an empty array. Now we'll be storing these calculated values inside that table. Let's start. Fibonacci of 5. We don't know what is Fibonacci of 5. So split it into 2. N minus 2 and N minus 1. Come down here to the left hand side. Fibonacci of 3. What is Fibonacci of 3? We don't know. Split it again into N minus 1 and N minus 2. Fibonacci of 1. What is Fibonacci of 1? Is 1. So here store the value 1. Next, Fibonacci of 2. This value less than or equal to n, condition is false. Again split it into 2. I have Fibonacci of 0, Fibonacci of 1. What is Fibonacci of 0? It is 0. Fibonacci of 1. I have already calculated Fibonacci of 1, so this will not be called. I will be directly fetching this Fibonacci of 1 value from this table where it is stored. So it is 1 plus 0 is 1. Now I have the value of Fibonacci of 2. What is the value of Fibonacci of 2? 1. So store that value here. Next, go to the right hand side. Fibonacci of 4. Do we know the value of Fibonacci of 4? No, we don't know it. Come down here. Split it. Fibonacci of 2 plus Fibonacci of 3. What is Fibonacci of 2? We have already calculated. What is its value? So do not call this. The value 1 will be fetched directly from that table. So it will be 1. Next is Fibonacci of 3. If you come over here, this is 1 plus 1. It is 2. Left hand side. 1 plus 1 is 2. So Fibonacci of 3 is already stored in this table over here. 2. Now when I split this here into n minus 2 and n minus 1, I have Fibonacci of 3. Fibonacci of 3 value is already calculated and it is turned out to be true and it is already stored there in the table. So do not call this function. So all these functions will not be called. So 2 plus 1, it is going to be 3. So Fibonacci of 4. What is the value of Fibonacci of 4? 3. Fibonacci of 5, 3 plus 2. So now the number of function calls, recursive function calls, have been reduced. First, how many function calls did we do with normal recursion? It was 15. Now how many? 1, 2, 3, 4, 5 and 6. So from 15 it has come down to 6. So the number of function calls went down from 15 to 6. So the time complexity required or taken by dynamic programming is less as compared to normal recursion or normal problem solving. So for n value, if I take 5, the number of function calls is n plus 1. N plus 1. So the time complexity of this is order of n. Is order of n. If you consider the previous recursion technique, it is 2 raised to n. So it is exponential. So recursion time complexity was exponential 2 raised to n. It has come down to linear. So the time complexity has greatly reduced with the help of dynamic programming. So this is how the problem of overlapping sub-problems is reduced. How it is reduced? By taking a table and calculating values. So whichever sub-problems values are calculated, those are stored inside a table or an array. And whenever the need for those values is required, it is not recalculated. Those values are fetched from the table itself. So this is dynamic programming. Now let us see how to solve this problem using iteration. Generally, to solve dynamic programming problems, we do not use recursion, we use iteration, we use loops. Recursive function calls are never used for dynamic programming. Okay. So how to solve this program using iteration? So I have function Fibonacci of n. I'll say a of 0 is equal to 0, a of 1 is equal to 1. For I equals to 2, I less than n, I plus plus, I'll say a of n minus 2 plus a of n minus 1. I'll say return a of n. So this is a program or an algorithm for solving Fibonacci or getting the nth Fibonacci number using iteration. Right. So this iteration, again we are going to use a table over here, and we're going to go on storing those values. Index value 3, 4, 5. Let's see. A of 0 is equal to 0. A of 1 is equal to 1. Next, I value starts from 2. So I will start from here. Less than n, yes, condition is true because n value is 5. N minus 2 plus n minus 1. This is n minus 2, n minus 1. So this will be 1. I plus plus. N minus 2 plus n minus 1. 1 plus 1, 2. I plus plus 2 plus 1, 3. I plus plus 3 plus 2, 5. 3 plus 2, 5. So for solving problems using dynamic programming, recursion technique is not used, iteration is used. So this approach is called bottom-up approach. This approach of solving a problem is called bottom-up approach. See here, n value is 5. So to reach the value 5 or to reach the value n, we are starting from below, from the 0th element. So from 0, we are going to n. So this is bottom-up approach. Whereas in recursion, what we have seen, it is top-down approach. It is top-down approach. Because here we started with Fibonacci of 5, then we split it, we went to Fibonacci of 3 and Fibonacci of 4, and then again we split that, we went to Fibonacci of 1 and Fibonacci of 2. So this is top-down approach. We are starting from the n value and then we are going below to 0. So this is top-down approach, this is bottom-up approach. So dynamic programming uses bottom-up approach to solve a given problem. So this was the difference between using recursion, which gave us the problem of overlapping subproblems, and iteration. Here there is no problem of overlapping subproblems. So that is why iteration is always used for dynamic programming.